Hello, welcome back to part 2 of haloalkane and haloarenes. In this part, we'll discuss about nature of CX bond. Nature of CX bond. Here X is more electronegative, so gains partial negative charge. C is electropositive or less electronegative, so gains partial positive charge. This bond is polarized. You know, here X is fluorine, chlorine, bromine, iodine. Size of iodine is bigger than that of bromine. CX bond length increases from CF to CI. Here you see CF bond length is smaller than CCl bond length. CCl bond length is smaller than CBr. CBr bond length is smaller than CI. Bond enthalpies. Let us take an example. CS3F, CS3Cl, CS3Br, CS3I. The bond enthalpy of CS3F is 452 kilojoule per mole. This one 351, 293, 234 kilojoule per mole. So obviously bond enthalpy of CH3F is more than CH3Cl, is more than CH3Br, is more than CH3I. Then dipole moment. Let us take the same example. CH3F, CH3Cl, CH3Br, CH3I. Usually diplement of CH3F is 1.847 diby. This is 1.860 diby. This is 1.830 diby. This is 1.636 diby. Here dipole moment of CH3Cl is more than that of CH3F and CH3Br. Dipole moment of CH3F is less than CH3Cl. CH3Cl dipole moment of CH3Cl is more than that of CH3Br. CH3F, CH3Cl, CH3Br, CH3I. Dipole of CH3Cl is more than that of CH3F and CH3Br. Then methods of preparation of haloalkanes and aryl halides. Let us start. From alcohol and halogen acid. Alcohol means ROH. You see, this is alcohol treated with HX gives water, then R combines with X gives Rx. This is alkyl halide, or you can say haloalkane. You can take CH3OH and HCl gas, you'll get CH3Cl plus water. But here one thing you have to remember, this water combines with Rx to give back alcohol. To stop the reaction of alkyl halide with water, we have to treat this reaction with anhydrous zinc chloride. Anhydrous zinc chloride absorbs water. So the reverse reaction is not possible. So we should write ROH plus HX in presence of anhydrous zinc chloride gives alkyl halide and water. Alcohol is of three types: primary, secondary and tertiary. And HX is HCl, concentrated HCl, and this is anhydrous zinc chloride. Concentrated HCl and anhydrous zinc chloride is known as Lucas reagent. There are three types of alcohol: primary alcohol, tertiary alcohol. Let us take tertiary alcohol. Tertiary alcohol on treatment with HCl gives tertiary butyl chloride and water. So simply shaking tertiary butyl alcohol with concentrated HCl gives tertiary butyl chloride. Tertiary butyl alcohol on shaking with concentrated HCl gives corresponding chloride, and this reaction takes place at a room temperature. And secondary alcohol gives corresponding chloride after 5 minutes. You can take, this is a secondary alcohol on treatment with HCl in presence of zinc chloride gives corresponding alkyl chloride, that is secondary alkyl halide, after 5 minutes. Primary alcohol does not give alkyl chloride at room temperature. It needs boiling. So primary alcohol gives alkyl chloride upon boiling. Then ROH gives alkyl iodide by treating with sodium iodide or potassium iodide with 95% phosphoric acid. ROH gives RI by treating potassium iodide or sodium iodide with 95% phosphoric acid. phosphoric acid. So here we can get a conclusion: tertiary alcohol is more reactive than secondary alcohol is more reactive than primary alcohol with a given halo acid. Another note: aryl halide cannot be prepared by this method, or you can say when phenol is treated with HCl does not give chlorobenzene. Why? Because this CO bond has partial double bond character. Because of resonance. You see, this is phenol. Then what happens? This lone pair forms a pi bond, and the existing pi bond, this bond shifted over here. The existing pi bond, this bond shifted to this position. Here you will get partial double bond character. So to break this bond needs more energy. So reaction with HCl is impossible. So aryl halide cannot be produced by this method. This is aryl halide. This bond cannot be broken. Because of partial double bond character, and this partial double bond character is due to resonance. Here this double bond has more energy than single bond, so it is difficult to break a stronger bond. Then number 2, from alcohol, sodium bromide and H2SO4. You see, NaBr with H2SO4 gives HBr. This bromine and 1H gives HBr and NaHSO4. Then alcohol with this HBr gives water and RBr. So let us add these two reactions. You just put a sign of arrow mark. Then on the left hand side you have ROH, NaBr and H2SO4. HBr cancel, and on the right hand side you will get RBr, NaHSO4 and water. If you will take CH3OH with same reagent, you will get CH3Br along with same. Then third one, alcohol and phosphorus phosphorus trihalide. Alcohol and phosphorus trihalide. Here X is chlorine or bromine. So here alcohol, you have to take 3 molecules of alcohol, ROH, with here X can be chlorine or bromine. This 3 OH and this P gives S3 PO3, and each are combined with X to give 3 molecules of alkyl halide. 3 molecules of alkyl halide. So when alcohol is treated with phosphorus trihalide, gives phosphorus acid, orthophosphorus acid, and alkyl halide. Here we can prepare alkyl chloride by treating with phosphorus pentachloride. Next, when alcohol is treated with phosphorus pentachloride, gives alkyl chloride and POCl3 and HCl. You see, this is alcohol, just add with PCl, so you see this alkyl group combines with this Cl gives RCl. This H and Cl combines to give HCl, and POCl3. So when alcohol is treated with phosphorus pentachloride, it gives alkyl chloride, HCl, and phosphorus oxychloride. Next, number 5. Alcohol can give alkyl bromide or alkyl iodide by treating with red phosphorus with bromine or iodine. You see, alcohol on treatment with red phosphorus and bromine gives PBr3 in situ. During the process you will get PBr3, because PBr3 cannot be kept for a longer period as bromine atoms are bigger in size, so these bonds break easily. So this is an unstable compound. So it is prepared during the process. PBr3 in situ means when red phosphorus is treated with bromine gives PBr3 in situ, which on treatment with alcohol gives alkyl bromide. ROH on treatment with red phosphorus and bromine gives alkyl bromide. Similarly, when alcohol is treated with red phosphorus and iodine gives alkyl iodide. Red phosphorus on treatment with iodine gives Pi3 in situ. In situ means during the process. Next, number 6, from alcohol and thionyl chloride. Thio means sulfur, thionyl chloride is SOCl2. So when alcohol is treated with thionyl chloride gives ROH, S double bond Cl gives SO2, H with Cl gives HCl, R with Cl gives RCl. So when alcohol is treated with thionyl chloride, gives alkyl chloride in pure form. Why? Because this SO2 and HCl escape as gases. So RCl is produced in pure form. RCl is produced in pure form. This is the most suitable method to prepare alkyl chloride from alcohol. When alcohol is treated with thionyl chloride, gives alkyl chloride in pure form as SO2 and HCl escape as gases. This is the most suitable method to prepare alkyl chloride. Next, number 7, by free radical halogenation. Free radical halogenation. You see, when methane is treated with chlorine in presence of diffuse sunlight, you get CH3Cl, then CH2, Cl2, CH, Cl3, CCl4, as you have studied in 11th. So here you got methyl chloride, dichloromethane, chloroform, carbon tetrachloride. This is free radical halogenation. Here you can get mixture of mono and polyhaloalkanes, which is difficult to separate. It is difficult to separate the mixture of these compounds. Consequently, the yield of any compound is low. So when propane is treated with chlorine, we will get CH3, CH2, Cl and CH3CH, ClCH3 if monohaloalkane is taken into account. We will get polyhaloalkanes, but here we have taken monohaloalkanes. So here you got 1 chloropropane, 2 chloropropane. Here you got 1 chloropropane and 2 chloropropane. In case of butane, in presence of chlorine, halogen atom can be substituted over here or over here, that is like this, or at the middle position. So you will get two types of haloalkanes, monohaloalkanes. Write the number of monochloroisomers by the free radical monochlorination of isopentane. You know the structure of isopentane is like this: CH3, CH3, CH2, CH3, isopentane. Monochlorination means only one chlorine can substitute one hydrogen atom. So we can get the possible positions are either over here or here. Here you may get another monohaloalkane by substituting this hydrogen. Next, here you see I have given 4 colors, so you will get 4 products, but that is not the reason. These two methyl groups are identical, so here one H atom can be substituted, or here one hydrogen atom can be substituted, so you will get one monohalogen. If you write this Cl, over here you will get the same product, the name will be same, so you cannot get a different product. Then next one here you can substitute one H atom by a chlorine atom. Next, for this you can write one chlorine over here. Next, here you also substitute 1, 2, 3, 4 products, and just I have given the skeletons, so you can write the exact structure by putting hydrogen atoms, suitable number of hydrogen atoms. Then electrophilic substitution. By electrophilic substitution you can get aryl halides. You take, this is toluene, just treat with X2 in presence of Fe in dark position, in dark condition. X can be substituted the orthohydrogen atoms or the parahydrogen atoms. These are ortho positions, this is para position. So here we can get ortho-halotoluene. If it is at para position, we will get para-halotoluene, ortho-halotoluene, para-halotoluene, along with HX. Here the electrophile is X plus substitute ortho positions or para positions, and the ortho isomer, para isomer can be separated due to large difference in their melting point. Here X can be Cl or Br, or you can say aryl chloride or aryl bromide can be easily prepared. Aryl chloride or aryl bromide can be prepared easily in presence of Fe or Lewis acid. Electrophile is X plus, or you can say Cl plus or Br plus. Here Lewis acid maybe FeCl3, or you can say iron 3 chloride. However, reactions with iodine is reversible. So here, to make it irreversible, an oxidizing agent HNO3 or HiO4 is used. HNO3 or HiO4 oxidize Hi during iodination to I2. You see, suppose this is toluene, you treat with iodine, but the reaction should be carried out in presence of HNO3 or HiO4. HiSO produced will react with HNO3 or HiO4 to give back iodine. So the reaction becomes irreversible and the yield of iodobenzene, the yield of aryl iodide can be increased. Fluorocompounds are not prepared by this method due to high reactivity of fluorine. Fluorocompounds are not prepared by this method because of high reactivity of fluorine. Fluorine is highly reactive. reactive. So fluoro compounds cannot be prepared by this method. Next, Sandmeyer's reaction. Sandmeyer's reaction. You see, this is aniline when treated with sodium nitrite NaNO2 and cold dilute HCl at 0 to 5 degrees centigrade. You get benzene diazonium chloride. You get benzene diazonium chloride. Benzene diazonium chloride. You can say BDC, benzene diazonium chloride. This benzene diazonium chloride on treatment with situ Br2 or Cu2Cl2 gives bromo or chlorobenzene along with nitrogen. Or you can write like this also. Take benzene diazonium chloride. Instead of chlorine you write X over here. Then in this position you just write X. Here also you write X, then you will get bromo or chlorobenzene by treating with Cu2X2, and here this bromine chlorine can be written as X. Here X is chlorine or bromine. When aniline is treated with sodium nitrite and HX gives benzene diazonium halide and it becomes benzene diazonium halide. Benzene diazonium halide. Next, iodobenzene can be prepared easily. Replacement of diazonium group by iodine does not require the presence of cuprous halide. The cuprous halide is not required for iodobenzene. On treatment with potassium iodide, it gives iodobenzene directly. So replacement of the diazonium group. This is the diazonium group. Replacement of diazonium group by iodine does not require Cu2X2 or cuprous halide, and done by simply shaking the diazonium salt with potassium iodide. This iodine can substitute over here and this diazonium part can be removed. Then from alkene and halogen acid. You see, suppose this is CH2 double bond CH2, you add HX, one H will be added over here, one X will be added over here, and this double bond becomes a single bond. So CH2 becomes CH3, double bond becomes single bond CH2X. Next, If it is a non-symmetrical grouping, you treat with HX. Negative part will go to the carbon atom which contains less hydrogen, and positive part goes to the carbon atom of the double bond which contains more hydrogen. You see here there is one hydrogen, here there are two hydrogen atoms. So you will be getting CH3CHX, and the double bond becomes single bond, and CH2 becomes CH3. This is according to Markovnikov's rule. You know Markovnikov's rule. CH3CH double bond CH2. Here we will take HBr only in presence of benzoyl peroxide. Markovnikov's rule is reversed. Bromine goes to the carbon atom of the double bond which contains more hydrogen, and positive part goes to the carbon atom of the double bond which contains less hydrogen, and the double bond becomes single bond. So you see CH3, then this single bond, then this CH becomes CH, and one H atom will be added over here. So CH becomes CH2, double bond becomes single bond, then CH2, then CH2 bromine. Let me write again CH3, CH2, CH2 Br. This is anti-Markovnikov's rule. This is anti-Markovnikov's rule. Here it is applicable for HBr only, not for HCl or HI. But Markovnikov's rule is applicable for HX, HCl, HBr, HI, or any polar molecule can be added along with unsymmetrical alkene according to Markovnikov's rule. But here we are preparing haloalkane, so here we have to take HX. But for other polar molecules, Markovnikov's rule is possible. But anti-Markovnikov's rule only for HBr, not for HCl or HI, because HBr gives free radical, but HCl does not give free radical. Because it is a strong bond. HI gives free radical, but iodine free radical combines with another iodine free radical to give back I2. So HBr is applicable because anti-Markovnikov's rule follows free radical mechanism that you read in 11th. But Markovnikov's rule is an ionic one, follows ionic mechanism, but anti-Markovnikov's rule follows free radical mechanism, and HBr gives free radical only. HCl doesn't give free radical because it is a strong bond. HI gives free radical, but one iodine free radical combines with another iodine free radical to give back I2. So it does not show the addition of HI with unsymmetrical alkene in anti-Markovnikov's. Next, addition of halogens. You see CH2 double bond CH2, addition of halogens, addition of halogens. CH2 double bond CH2 plus bromine in presence of CCl4, carbon tetrachloride. The color of reddish brown color of bromine CCl4 gets discharged. One bromine is added here and the other bromine is added over here, and the double bond becomes a single bond, and you got CH2 CH2 Br. Here addition takes place. Here addition takes place. Double bond becomes single bond, and the reddish brown color gets discharged. So it is a test for unsaturation. This is unsaturation part in alkene. If there is unsaturation part on treatment with bromine and CCl4 gets discharged, so it shows that there is a double bond or unsaturation in that hydrocarbon. And this is your vicinal dibromide, because two halogen atoms are bonded to adjacent carbon atoms, and you know what do you mean by adjacent. And this is colorless. This is colorless. So bromine CCl4 is added to alkene to test the unsaturation. Unsaturation means presence of double bond or triple bond. Here we are concerned with double bond, so bromine CCl4 is used to test the unsaturation in an alkene. Next halogen exchange. Halogen means, you know, chlorine, bromine, iodine, fluorine. So you see Rx, here X is chlorine or bromine. That is important. You see here Rx is alkyl chloride or alkyl bromide. When treated with sodium iodide in dry acetone, what happens? Now this X gets exchanged with this iodine, and you are supposed to get Ri, and this X combines with Na gives NaX. Here X is chlorine or bromine. So what is the use of dry acetone over here? Now dry acetone keeps sodium halide in precipitated form. Alkyl iodides are often prepared by reaction of alkyl chloride or bromide with sodium iodide in dry acetone. This reaction is popularly known as Finkelstein reaction. You remember? Finkelstein reaction. You see, one trick will be given over here. Here you have exchanged iodine. In Finkelstein, you see I is over here. So it is easy way to remember. In Finkelstein, I is there. So here it is used to exchange iodine with chlorine or bromine. This is a trick. So when alkyl halide is treated with sodium iodide in dry acetone, you will get alkyl iodide, and the sodium halide so produced is precipitated out in dry acetone. Next, so if it is precipitated out, the yield of Ri will become more, or you can say forward reaction is favored in presence of dry acetone, according to Lee-Chatelier's principle. So the yield of alkyl iodide is more in presence of dry acetone, or the forward reaction is favored because of Lee-Chatelier's principle, by the help of Lee-Chatelier's principle. Then synthesis of alkyl fluoride. Usually fluorocompounds are not prepared because fluorine is highly reactive, but here is a method to prepare alkyl fluoride. How you see? You take Rx, here X is chlorine or bromine, treat with silver fluoride or mercurous fluoride or COF2 or SbF3, then this X is exchanged with this, so you'll be getting RF. So here one example can be taken, CS3 beer treated with silver fluoride gives CS3F plus AgBr, and this reaction is known as Schwarz reaction. This reaction is known as Schwarz reaction. In Schwarz reaction, you can get fluoro derivative. Bromine is substituted by fluorine, so you get fluoro derivative. One important example is there for Schwarz reaction. Freon 1,2. Freon 1,2 means CCl2 F2. Freon 1,2 means CCl2 F2. This CCl2 F2 Freon 1,2 can be synthesized from tetrachloromethane means CCl4 by Schwarz reaction. You see here we have exchange X with F. Here X is chlorine bromine, but here I have taken CCl4. Here there are 4 chlorine atoms, but here there are 2 chlorine atoms and 2 fluorine atoms. So 2 chlorine atoms are exchanged by these 2 fluorine atoms. Here you see here there are 4 chlorine atoms, and here 2 chlorine atoms are exchanged by 2 fluorine atoms by Schwarz reaction. So Freon 1,2 can be synthesized from carbon tetrachloride by Schwarz reaction. One interest question is there: why is sulfuric acid not used during the reaction of alcohols with Ki? Sulfuric acid is not used during the reaction of alcohol with Ki, but you use S3PO4. Why? You use S3PO4, 95% phosphoric acid, but not H2SO4. Why? The reason is very simple. H2SO4 cannot be used along with potassium iodide to convert alcohol to alkyl iodide, because H2SO4 converts Ki to corresponding Hi. Ki is converted to Hi, oxidized to iodine by sulfuric acid, and Hi oxidized to iodine. So here H2SO4 cannot be used along with Ki to convert alcohol to alkyl iodide, because H2SO4 converts Ki to corresponding Hi, and Hi is by H2SO4 to I2. Next question: write the structures of different dihalogen derivative. Dihalogen derivatives of propane. You see, this is propane, this is primary carbon, this is primary, this is one secondary. So you can get like this, or you can write X over here can put 2 extra atoms in second carbon, but no need of writing over here because this structure will be same as that of this one. So here you can write geminal dihalides. So there are two types of geminal dihalides. Next, you can put halogen over here, so you can get vicinal dihalide. You can get like this also. Then there are 4 types of products. You see, you get 4 types. Among the isomeric alkanes of molecular formula C5H12, identify the one that on photochemical chlorination gives a single monochloro derivative. So C5H12 means you will get 8 types of monochloro derivatives. Among the isomeric alkanes of molecular formula, identify the one that on photochemical chlorination yields a single. Among the isomeric alkanes of molecular formula C5H12, single monochloride. Single monochloride means you see there are 3 types of isomers of C5H12. Single monochloride means this one gives single monochloride because all the carbon atoms are identical to the neocarbon. So you can get a single monochloride, but here you can get 3 types of monochlorides, 1, then 2, then 3. You will get 3 types of monochlorides like this. But this compound gives 1 type of monochloro derivative, and this one can give 4 types, 1, 2, 3, 4. You see, I have given 4 types of signs. These 2 carbon atoms are identical, so you can get 1 monochloro derivative by putting chlorine over here or over here. Then by putting over here you will get another one by substituting this hydrogen atom, and by substituting over here you can get another one, by substituting over here you can get another one. So 4 types. So total there are 8 types of monochloride derivative, but single monochloride derivative is prepared by neopentane. Then it is given, this is a let me draw the structure again. Treat with SOCl2, you will get the product like this. This is thionyl chloride. Next, this is treat with bromine, then heat or UV light, and the product will be these H atom is substituted by a bromine atom. You see, then next this is an alcohol. Here OH is attached to the side chain, here OH is attached to the benzene ring directly. Then you treat with HCl, and give heat. HCl gas, and you heat it, then this chlorine will substitute this OH or this OH. That is matter of debate. You know, I told earlier, this lone pair on oxygen can form a double bond over here, or you can say partial double bond character. Partial double bond character will be there. So this lone pair will form a partial double bond, or due to resonance, because of resonance, so it is a stronger bond. But no resonance is possible over here. This is a simple sigma bond or single bond. So this OH can be replaced or substituted by this chlorine. So you are supposed to get OH CH2Cl, and this OH with this H gives water molecule. Next, treat this one with HI. You see, at this position there is only one carbon, that you know, but no hydrogen atom, because you see there is a double bond, and this carbon 1 2 3 4 bonds. There are 4 bonds, and this one del plus del minus, and this I can bonded over here, and S can be bonded over, and this is according to Markovnikov's rule. I being electronegative added to the carbon atom which contains less hydrogen. Here you see there is no hydrogen. Here this carbon has no hydrogen, but this carbon has one hydrogen, but here no hydrogen. So iodine prefers to attack the carbon atom which contains less hydrogen or no hydrogen, and H will prefer to attack the other part of the double bond. So the possible structure is like this. This double bond becomes a single bond, and here 2 H atoms are there. Double bond becomes a single bond. CH3 is there, and iodine is, or you can write the structure like this also. Next, you take CH3 CH2Br, treat with sodium iodide in dry acetone. Then iodine exchanges Br, and you are supposed to get CH3CH2I, and the NaBr so produced in dry acetone gets separated out as a precipitate. This is your Finkelstein reaction. Here iodine is there, here iodine is there, and this iodine is substituting this bromine or exchanging this bromine. Next, This is cyclohexene. Treat with bromine, heat or UV light. It gives free radicals, so it doesn't show addition reaction. It will substitute the hydrogen atoms. It cannot be added over here. It cannot be added over here. So you are supposed to get or you can write like this also. Hope this video will help you a lot. In part 3 of haloalkane, we'll discuss from physical properties. Thank you for watching the video till the end.